Good afternoon, everyone. My name is Ahmad Faqiri. I work for HDR Vienna office, and it's good to be back in Delaware. I started my career at Dell.dot, so I see some familiar faces here. I'd like to thank the Northeast Bridge Preservation Partnership for giving us the opportunity to present our project. I also like to thank Dell.dot for hosting this conference. Back in January, when Jason Hastings sent us an email notifying us about this conference, I thought that we had a good story to share with you folks as well. So today, Jeffrey Hollands and I will be talking about the rehabilitation scheme for Southeast Southwest Freeway. It's also known as I-695. This is a DDOT project located in the heart of our nation's capital. Throughout this presentation, I'll be introducing the project, and Jeffrey will be talking about some of the unique repairs and retrofits that we used for this project. Schedule-wise, it's worth noting that we're in the final design phase of the project, and hopefully one day we'll come back and talk to you about construction phase, and our presentation will be as lively as Kevin's presentation. So, as you can see from this aerial photo, the project is about half a mile of bridges and ramps. These bridges span over public parkings, South Capitol Street, if you're familiar with DC, developers' properties, New Jersey Avenue, and CSX facilities. The bridges were built in the early 1960s and were rehabilitated in the early 1990s. The traffic volume on this corridor is 134,000 vehicles a day, and it's anticipated to increase by 35% in the next 20 years. Although these bridges are not considered historic, the project is in the middle of many historic landmarks. The Capitol, National Mall, Capitol Hill, this historic district, just to mention a few that are within a mile or two radius of the project. There are public parks, namely Garfield Park and Randall Field, adjacent to the bridge, and there are also residential buildings near the project. The bridge serves as a main access point to many sports location. Most notable are the Audi Field Soccer Stadium and the national parks. As you can imagine, there is a lot of interest from stakeholders as well as local political entities. This color plan view gives a good idea of the main bridge and its associated ramps for the project. Starting from the left or the west side of the project, the red area indicates Bridge 1103. This bridge is, and its ramps are comprised of series of simple span, pre-stressed post-tension. Yes, they're pre-stressing and post-tension in the same beam. Tension concrete beam structures. The yellow area is Bridge 1104, and this bridge and its ramps are comprised of series of steel girder bridges. The span over South Capitol Street is cantilevered beyond the piers, and it has pin connections on the outside spans of the bridge. The green area is Bridge 1109. this bridge is comprised of series of steel multi-girder structures with steel pier caps. DDOT, as I mentioned, is the owner and our client. HDR is the prime responsible for structure designs, roadway design, sign structure repair designs, traffic study, MOT plans, drainage design. Panoni Associates and ALA helps with structure design of the ramp bridges. Inspire Green provides environmental permitting and public outreach. Salute provided geotechnical exploration and laboratory testing. CV Inc. Provides survey and utility designations. Olson did parallel seismic testing. This is essentially drilling a hole next to the substructure or next to the piles and sending down a probe while hammering on the column to determine the length of or the depth of the piles. The as-built plans for this project did not have that information, so we needed to get that. Indesco provides lighting design, and we are in the process of adding KCI to our contract to conduct value engineering for this project. This is a requirement for bridges over certain construction costs. As you can see from these two aerial photos, span over ramps and the CSX lines, those dark lines are joints for the bridge, and you can see that the bridges are skewed very heavily in certain location. In some of the cases, the spans are actually triangular. They have very odd shape, and that makes the rehabilitation a bit challenging. As you can see, there are few pinch points on this corridor where you have virtually no shoulders or very small shoulders and only 3 lanes. There will be three-phase construction on the main line, and we must maintain 2 lanes of traffic at all time. And some of the ramps will be repaired under temporary off-peak hour closure. So traffic control is going to be one of the risk item on the project, and seeing some of those issues that you guys had with the Wilmington Viaduct and the I-95, it's very good to hear that we can hopefully go through this project as well. Here we wanted to show most of the type of deterioration throughout the project. As you can see, there are parapets that have damaged delamination or cracks on them. Typical deck crack and delamination throughout the project, and joint failure. Almost every joint on that bridge, actually every joint on that bridge is failed. There are still beam corrosion throughout the project. Pre-stressed concrete beams have cracked due to post-tensioning duct corrosion. That's that one picture right there. And spalling of the concrete mostly near the bearings on the pre-stressed beams. That's the middle picture right there. Did I just advance? Right there, that picture. All right. Steel and concrete diaphragms exhibit deterioration, whether it's corrosion or cracks in them. And then you have steel bearings, and sign of deterioration on the steel bearings, and also some elastomeric bearings that show the same sign of deterioration as well, and they need to be replaced. As you can see from these images, we have pier caps that needs to have delamination and corrosion of the steel reinforcement, and columns with delamination and spalling as well that needs to be repaired. Now I would like to hand it over to Jeffrey Hollands to talk about some of the state-of-the-art solution we're providing for this project.
Thanks, Ahmad. So as you can see, lots of variety of structure types out there, lots of types of defects, so leads to lots of rehabilitation efforts going on. I'm going to talk at a high level quickly through most of the signature items that we're going to cover as we're designing the repair for these bridges. So DDOT expressed interest in the use of UHPC for some of these repairs, and so we're moving forward with a UHPC deck overlay at this time for the structure. In the testing of the deck that was done, they found evidence of some ASR, mostly in a shallow condition. So UHPC will be able to be a more shallow overlay, but since it's such a low porosity material, it'll also provide that protection from the chlorides in the de-icing salts. One of DDOT's other concerns with the overlay is they've experienced a lot of cracking in overlays done with more traditional materials. So they're interested in the improved cracking resistivity that you can get from a UHPC material. We'll also use UHPC for the joint closures that we're doing. Many of the joints on the bridge have been closed, or the eligible ones at this time in the previous rehabilitation, but there's a couple that we can add to. The main benefit that we're looking at for these UHP link slabs is that you get to have a partial depth demolition, which increases the construction speed, so you don't have to demolish quite as much material, and you also get the benefit of some built-in formwork from the existing deck already being there. I understand we're going to learn a bit more about UHPC link slabs, I think, tomorrow, so I'll leave it there on this one. As Ahmad mentioned, there's some diaphragm cracking. You can see the lateral cracks in that top photo there. When they did the joint closures in the previous rehabilitation in the 90s, they created very large, rigid diaphragms between the pre-stressed beams that are almost the full width of the pier caps and rigidly connected with anchorage into the pier caps. And so over the 30 or so years since those have been put in place, the natural movement of the beams under live load and temperature expansion has fought against that rigidity that was built in, and so we've got these cracks that have appeared, and our approach to hopefully put some of that flexibility back into the system while maintaining that joint closure is that we will demolish a portion of that oversized diaphragm and build it back to just at the top of the bulb from the pre-stressed beam so that you can get a little bit more of that natural movement and the bearings can do what they're meant to do. If you can look in the bottom photo there, you can kind of see the bulging elastomer. It's quite thin, but they've also had issues with those starting to slide out the bottom. So by deconnecting the diaphragm from the pier cap, we can now get access to those bearings to replace and add some new elastomeric bearings back in. Ahmad mentioned the longitudinal cracks in the bottom of the pre-stressed post-tension beams. These started developing about 20 years ago, and at that time, DDOT explored by removing the bottom of one of the beams to see what was going on. And what they discovered at that time was that the concrete itself, as well as the pre-stressing strands, were in pretty good condition. But as you can see from the top photo, that post-tensioning duct has a lot of corrosion, which when that expanded from the corrosion, introduced the longitudinal cracks into the beams. From what we've discovered in the as-built is the two top post-tensioning decks daylight at the top of the beam and then are encased in the deck, so they're not exposed to any water intrusion. but the plug at the end of the bottommost post-tensioning duct, any cracks or failure of that in the open joints, then water can start to slowly intrude through the grout. They did discover that the grout had cracks and gaps in it. So over the 60 years since this has been constructed, that post-tensioning duct has corroded. And so in order to reintroduce the strength that was lost from that corroded post-tensioning, we will be adding FRP strengthening to the bottom of the beam. And then in addition to that, we'll be using the discrete FRP wraps up the side of the beam to offer some confinement to that bulb, because if you see from the previous photo, there's no confinement reinforcing anywhere in this beam, so protect the public down below in case there's any further deterioration. For the steel beams, since we'll have UHPC contractors on site, we're going to use UHPC to repair some of the deteriorated steel beam ends. The way this works is that you weld shear studs in an array around the deteriorated steel and then cast a block of the UHPC around those shear studs to get composite action between the concrete and the steel and transfer the loads that would have been in the steel to the concrete. And the concrete has that compressive and slight tensile strength because it's UHPC. The added benefit of this is that when you're encasing the steel in the concrete with this low porosity, you get a protective coating around the steel to hopefully reduce any further deterioration of that steel. As Ahmad mentioned, there's lots of high skews and stuff, so this is extra ideal when you have complex geometry. It's easier to form the UHPC in those tight spaces rather than having to work with a traditional steel plate type repair, which we will use elsewhere on the structure, but where the UHPC makes sense, we will be implementing that. There are those pinned connections that Ahmad mentioned on two of the structures, the 1104 and 1109 steel structures. The 1104 structure, which is shown similar to the image on the bottom of the screen, that one's from another project as an example, but that one is a pin and hanger type connection that's mid-span between two longitudinal beams. And so we'll be implementing a fairly standard catcher beam there as a sort of a additional protective measure in case that non-redundant pin and hanger connection does fail. Hopefully this catcher beam never needs to be used, but if the pin and hanger does fail from fatigue loading at any time, then the catcher beam is there to prevent a catastrophic failure of that beam dropping away. The other type of pin and hanger is at those steel pier cap cross girders on the 1109 structure. So if you look at the top photo, you can see that that deeper cross girder would prevent the implementation of the standard catcher beam. So we're developing a corbel type approach where the corbel will be attached to the cross girder and sit as a seat for that longitudinal girder. We are fortunate that none of the pin and hanger locations have any sort of vertical clearance concerns, so we have the space to implement this catcher beam, which is a more cost-effective solution than some of the other options we have for rehabilitating the pin and hanger connection. It's cheaper material rather than trying to, develop a new connection between those longitudinal girders, or to reorient it so that the suspended span now rests on top of the supporting span. Those are two other options that we explored. The other benefit of the catcher beam is that you can reduce how much deck you remove up top and then reduce the impact on the traffic, which is our major cost concern for this project. Lastly, we'll be adding metallizing treatment to some of the most deteriorated concrete pieces on the structure. The way this works is similar to those galvanic puck anodes that are very regularly used in concrete repairs. A aerosoled metal coating is applied to the outside of the concrete, and it is formed with a metal that is less noble than the steel reinforcing, and then some electrical continuity is connected from the coating to the reinforcing steel. Those chloride anodes that would cause the corrosion of the reinforcing steel are extracted out into that sacrificial metal coating. The main benefit of this over the galvanic puck anodes is it has a slightly longer service life, and it provides that full coating around the structure, which can add some additional protection to the concrete that has not yet spalled or deteriorated, whereas the puck anodes are typically would only be added where the concrete is getting repaired. So with that, I will open it up to any questions. Went back there.
Yeah, a question on the cross-bracing steel corrosion repairs with ultra-high performance concrete.
Yeah.
Is there any tips and techniques or anything like that that you could offer in addition to what you're speaking about when repairing that deteriorated steel with high performance concrete?
Sorry, do you have anything specific in mind?
Yeah, where there's diaphragms in that cross girder, stuff like that. Attaching the shear studs. How much good section do you need to have the stud shot on there and stuff like that?
Sure. So the exact amount of necessary steel would be, it's somewhat dependent on the loads that that diaphragm is seeing or the end of the beam is seeing. Certainly something with lower skews where you're not going to be having to take on as many loads. You can apply it in a smaller area. If you're dealing with a highly skewed or curved bridge or something, you're going to need much more strength transferred over to that bridge. So I would say at this time, until it's in its infancy as an approach, but for the time being, it's somewhat of a context-sensitive solution, and it's not going to discount the standard steel repairs or even replacements. We are using them on this project. There are absolutely times where it's still applicable, but I hope that answers your question. Yeah, yep.
Yeah, the metallizing on a concrete, I hadn't seen that before. Have you utilized that elsewhere, or is that a first-time application?
This will be our first time using it here in our mid-Atlantic region where Ahmad and I are from. We have corrosion experts at HDR from our Florida office who have used it extensively in the marine environments on their columns down there. So there's been proven successes, particularly our Mercedes, our corrosion expert, said there. Places like Washington State, they've experienced good uses with it, Oregon, the Pacific Northwest. Those marine environments are where it seems to be the most applicable, and they've had great successes with it.
Okay, thank you.
Mm-hmm.